Get the file loaded to, we'll be good to go. And we'll kind of move quickly through data screening again because it hasn't really changed. We've actually already data screened this set, but it's going to be slightly different because what we're doing today is interactions. So we spent most of the semester talking about ANOVA is just a fancy form of regression. And with ANOVA, we look at main effects, each variable by itself, and interactions where the variables, the different levels of the variables have different effects. And so we spent a lot of time talking about how you split them down, you break them down, and then you analyze them by one group or another. But with moderation, the problem is often you're dealing with continuous variables. There are no more groups. So I can't really split into separate data sets because it's just one continuous group. So we're going to use that same books and attendance one because it works and it runs, and look at the interaction between books and attendance. So maybe if you're reading a lot of the books, you don't have to go to class. Or maybe if you're doing both, your grade is getting much higher. There are some special things with moderation. And the first thing is centering. When you create an interaction variable, all you do is multiply them together. So I take whatever your score is for attendance, whatever your score is for book, and multiply them. And the package we're going to use will do that for you. Oops. Well, what that means is that you're creating multicollinearity. Okay, you're ruining additivity, if you will, because they're a perfect, what's what I'm looking for here, perfect transform of each other. So we've talked a little bit before about don't use each individual item and the total score in analysis because it'll freak out, because the total score is just all those items added up. So they're perfectly correlated. If I have two columns and then a column of their interaction, they're perfectly correlated. But that's the point of this analysis. So how do we solve that problem that we're creating multicollinearity, or we're ruining additivity, if you will? Instead, we're going to center them. Center them. There's two types of centering. There's lots of types, but the two main types of centering are mean-centered and z-scored. Hey, squeak. So let's say we have just a simple analysis of books by grade. And people can read 1 to 6 books. Okay, and our grade ranges from 0 to 100. A mean center, this would be the original scale. And so people, the more books they read, the better their grade. A mean center is where we would just subtract the mean from everything. Okay. So let's say the mean is 3 books to make this nice and easy. 3. I said 3. I can't. 3 minus 1. 1 minus 3 is negative 2. So a mean center is where we just take our mean that I made up as 3 and just subtract it from everyone's scores. What does that do? That means that the average score is now 0. And if your average score is 0, that basically takes that intercept and moves that over. So it makes it easier to interpret. So the B value in a mean-centered analysis is what happens when people are scoring on average. So all you're really doing is shifting from the original scale to a centered scale where 0 means that somebody got an average score. That's very similar to z-scoring. With z-scoring, we then divide by the standard deviation. And when you z-score something, it becomes beta. So we go from it being b to beta. And so let's say the standard deviation is 2, because math is hard. (1.5) 2 over 3. 3 over 2. 1.5. Sorry. Math is hard. Okay. I don't know why simple math is so much harder now that we have calculators and phones. But in a z-score distribution, 0 still means that I'm on average, because we've transformed this from, instead of saying, well, I read 3 books, it's I've read an average number of books. But in a mean-centered analysis, 1 point is still 1 point in the scale. So each one of these points is 1 book. In a z-scored analysis, each one of these points is 1 standard deviation of books. So this is 2 books here, because it's 1 standard deviation, which is 2 points. Both are very popular for moderation analysis, but either way, you gotta do it. And it helps solve a multicollinearity problem. It also helps interpretation for simple slopes, which we'll get to towards the end. So if we z-score them, it creates a mean of 0 and a standard deviation of 1. If you just mean center, it creates a mean of 0. The standard deviation stays the same as the distribution. The real problem is if you don't center them, it says the beta values may be negative. This should say B or beta, really. If you don't center them, the scores for the slope, your coefficients, they may be negative, but on the picture, it'll look positive. And you'll be telling people, well, there's a negative relationship between my drinking example from before, drinking and depression, and then on the graph, it goes up. And people look at your graph going, what? Okay. So it also helps with the graph. Makes your figure match the picture you're expecting. And then when they're centered, the means will be 0 and the B values will match. So this should also be B beta. Cool thing is, Quantpsyc, the package we're going to use for this, will center them for you. Okay. Quantpsyc does a mean centering. I finally decided I like mean centering better because then the B values are at least in the original scale of the data. But either one's perfectly acceptable. Okay. And so it's essentially the choice between B and beta. Just like in a regular regression, you have a choice between B and beta. So if you want B, mean center. Or if you want beta, z-score. So we're going to center them for 2 reasons: interpretation and multicollinearity. I should probably write that down. Okay, so centering, two reasons: interpretation. You can say additivity or multicollinearity. They're the same thing. One's good, one's bad.
Will you repeat that?
Yes. 2 reasons to center: interpretation, and it solves multicollinearity, or it solves multicollinearity is easier than saying it helps with additivity. It sounds weird. Okay, that's fine. Because the interpretation is probably the harder one, but we're not quite there yet, so I'm going to talk more about that in a little bit when we get to simple slopes. All right, so the reason it causes you a problem to put the interaction in is because it's perfectly multiplied. So I just multiply participant 1's book times their attendance. Slight typo there. Instead of grades, you should say attendance. Their book score times attendance. You do not center the DV. Okay, you don't touch the DV. We're rescaling the IVs, not the DV. You can't rescale both. It'll freak out. The interaction is created after they're centered, so the interaction is centered as well. So it is centered, then made. And the point of moderation is to really understand that interaction. So with mediation, the point was like step 1 to step 2 to step 3. Moderation is about the different effects you get at different levels of the variables. I'm going to use the word level because there's not a good corresponding word, but it is not literally a group. So by levels, I mean like the different strengths of the variable, not different groups. There are no groups here. Zilch groups. Okay. That's one of the important things to get. Okay. So for power, we're going to use the same one we did for mediation. So I've got t-test linear multiple regression, fixed model, single coefficient. So just like with ANOVA, when we were talking about power, I said, why would you, if you include both variables, you clearly want the interaction. I mean, maybe sometimes you don't, but generally you do. Otherwise, you wouldn't put both the variables together. So you test power for the interaction. So we were always talking about power for the interaction because that's the thing I care about. Same thing here. Why would you include an interaction and give yourself the headache of simple slopes if you didn't care about it? So we're going to use power for the interaction. So it's linear multiple regression, fixed model, single coefficient. That's what we did last time for mediation when we talked about picking the smallest effect. So we still want two tails. One tail's cheating. Hit determine, direct, and I think today I picked a large effect size, so 0.25. I should probably mix this up, but I'm blank. It's easy to pick a number you're familiar with, right? So a large effect of this interaction, so 0.25. Calculate and transfer to main. We've got alpha, it's 0.05, power is 0.8. And the number of predictors, very tempting here to do 2. I got books, I got attendance. And the interaction, it's actually 3. So that's a part here that's going to be a little different. So the total number of predictors is 3 for simple moderation. Okay, when I say simple moderation, that means no other variables. You could covary things. You could do this as a step analysis where you first control for age and previous GPA and all these other things, and then do the interaction. Okay. So it's 3 if you only have these 3 variables. What people do is they forget there's an interaction. I've got books and I've got attendance, great. 2. Well, you're actually missing out on the one you're testing for, which is the third one. Okay, so it should be 3. And if it is truly a large effect size, we would only need 26 people. And we have 40. Fingers crossed it's a big effect. It is, because it's made up data. So that's what I'm saying. Moderation examples are hard to make up, and I have like 4. And I just cycle through them in my classes. They're hard to come by. Okay. So what we did for mediation was we did one or 2 predictors, and you pick the smallest effect size. For moderation, you're talking about just the interaction usually. So all this stuff that we've done like 1,000 times now, we're just going to kind of scroll through. So the data can't be negative. We've screened this data set before, so it's still fine. There's no negative books or attendance. Grades are 0 to 100. But this here is new. So line 10. I have no missing values, so I'm going to skip this part. Now I said Quantpsyc will center it for you, and it doesn't really want to do the assumptions for you the way we've been doing them. So at this point, you're supposed to stop and run the final analysis. Well, I don't want to scale my variables before I put them into Quantpsyc. You can, but then it'll scale them again, which is a little weird. So what you want to do is only scale them like here, and that's just a temporary placeholder for your analyses. But if you don't, you're testing your assumptions on data that's not scaled, and then you're running the test on data that is scaled. So we're going to need to make match. So what you want to do, and this is where I'm at. So this is a lot of this is cut and paste, right? But this is one of the new pieces. So we use the scale function. It creates z-scores. So dv is scale x, where scale is false. I know that looks really funny. We've talked about this once before, so here's a reminder. Scale has 2 parts. Center equals true, that's the mean center part. And scale equals false is mean centering. Center equals true and scale equals true. Those are both defaults is z-scores. So I just left off center equals true because it's the default. But I turned off scaling because I'm going to do mean centering. So I don't want to test my assumptions on z-scores. I just want to make sure my assumptions test and my real analysis match. The other thing that you will notice is we used a little star. We did that when we did MANOVA and ANCOVA. Otherwise, you're just adding them, and it's just a simultaneous regression. That's the analysis we did several weeks ago at this point. So be sure you add the star. That'll multiply them. So this is just going to scale them while I'm using them, and you'll notice that they don't change at all over here under master. If you scaled them in the data set, what was that? Oh my God. If you scale them in the data set, it looks differently. Let me show you. That was intense, is what that was. True story. All right. Okay, so quick, just proof that nothing happened to the original data set. So when you scale something and save it, it saves how it did it. Scaled center. Okay. It actually tells you what the mean is too. And so let's say I actually z-scored it instead. Yeah, I'm typing at the bottom because I didn't need to save it. Okay. It actually shows you the mean and standard deviation. So you can tell if you z-scored something because it'll have this extra piece here where it says scale. And then if center is true, it tells you what mean it used. If scale is true, it tells you what standard deviation it used. We don't really want to fix our data set, though, because Quantpsyc is going to do that for us. And so by doing it here in the LM function, it didn't change my original data set at all. But it will help it make it match. So the nice thing is R does show you, like, hey, you scaled this data. It's not the same anymore. All right. So just proof that I haven't changed the data. All the rest of this is the same, though. So Mahalanobis hasn't changed. Okay, now for Mahalanobis, it does not screen the interaction. Okay, so it's using 3 degrees of freedom. Oops, did I get excited? There. 3 degrees of freedom, that's books, attendance, and grade. Okay. It doesn't really screen for the multiplication part. Okay. But Cooks and Leverage will. So we'll hit it with the more importantly on the slopes than on the pattern of scores. Because that interaction is a perfect transform, Mahalanobis sometimes won't run because it requires it to not be perfect. Okay. So for Mahalanobis, we only screen the 3 variables. We're not getting the interaction component, but for Cooks and Leverage, we are, so it evens itself out. All right, so our outliers, no outliers. Woohoo! Hopefully that hasn't changed from the last time we ran it. Now for leverage, there are 3 variables. Okay. So K is 3 for books, attendance, and the interaction. So I would say that's where people mess up. I mean, at this point, most people can cut and paste the code and you're okay. But K here, remember, is 3 variables. Even though you've only typed in 2, you have that 3rd interaction component. So we got 3 leverage outliers. And then I don't think any cooks. We really don't have any outliers. But if I wasn't sure, I would add them up and get rid of them. So I have 3 one-person outliers. And then all that code is the same. The only thing I had to change really was K to be 3. In mediation, it's 2, because there's X and there's M, and that's it. In moderation, there's X, M, and the interaction, so 3. Okay. I reran my analysis just on the new data set. Oh, no, I didn't. I cut and pasted code and then forgot to change it. So on page 49, guys, I have had a moderate amount of sleep. I still can't talk. Okay. I blame the accent on being in Texas for several days. So data equals no out here. It's not going to change anything because we didn't drop anybody, but if you do in your analysis, it would. So, okay. Remember, you're rerunning this with a new data set in case you eliminated outliers, so your pictures don't include outliers. Let's see. Okay, we've gone through all this, blah, blah, blah. This hasn't changed. Under additivity, we expect to have a problem. That's why we're centering the variables. If you don't have any other control variables, you expect there to be additivity problems. So you just kind of ignore it. If you have control variables, make sure they aren't too correlated. But we're doing simple mediation, so I left it in there so you'd have the code. Simple moderation, sorry. But I commented it out so that it wouldn't run. Okay. So if you end up needing this, you just backspace out the $signs. $signs, the hashtags, pound signs. What are the other options here? Number sign. It's got 3 different names. It's not a $sign. What? Oh, it has a name? It has a name. That's the name that I can't spell. All right. I'm going to go with pound symbol. All right. Maybe that's how you can determine someone's age. Ask them what that symbol is. Right? People used to dial on phones versus... Ooh, squeak. Okay. This part hasn't changed either, so let's just look at the pictures. Now it's a little weird because our fitted values are predictions of y on centered variables, but it doesn't hurt to center them again. So all it does is just shift to 0 again. So the pattern will still stay the same. This is bimodal, so that's not great. One thing on moderation analyses is that sometimes it's hard to meet the assumptions because you're assuming there's this interaction component. And interaction means that people have different slopes. It means that there is heteroscedasticity if you don't account for it. So sometimes the assumptions don't always look great because the point is that we're accounting for heteroscedasticity. So they tend to have worse looking graphs. So this is kind of bimodal. But most of it's between 2 and 2, and it's close to 0, so I'm saying it's all right. This not being very tall is not good. It's perfectly linear because it's made of data. But this looks good. And then this is okay. For homogeneity-wise, this spread is not so great. This way it's fine. This way, this 1 to 2, but really the problem is these screwballs out here. And then homoscedasticity-wise, it's okay. So I think if you go back and look at when we didn't include the interaction, the spread looks a little worse. When you do include the interaction, it helps fix it some. Okay, now we're on to the new stuff. So you want to load Quantpsyc. You should have that. We've used it for LM beta. So it's a package we've used a couple times. And hopefully I didn't screw up the order of my variables in this video, this version. But it could be. So we'll be sure to check. So we want to label what we want as X, M, and Y, just to start, just so we can make sure that I've done this right. So I think in mine I used books as X, M as attendance, and Y as grades. So can I switch these? Yeah. I think this is in the notes a little bit later, I think. But can you switch X and M? In this case, yes. Just like with an interaction for ANOVA, we have your 2 IVs. You could pick which way you want them to split, and we talked about it. Usually you pick the larger way, so you get a smaller number of tests. In this analysis, pick your favorite. The one you pick as M is the one you'll get the simple slopes for. Or the one you'll get group levels, strengths. Use the word levels loosely here. They're not actual groups. This one you'll get slopes for. So what'll happen is we'll have 4 high, low, average, and high levels of attendance. We will get book slopes, predicting grades. That's where we're going. So we talked about in ANOVA splitting the variables and analyzing, we've made those little post hoc boxes with like mean 1 and mean 2, but we had to split on one of them somehow. This is sort of that same idea of splitting. But we're not literally splitting them up. And we're going to get there in a minute. But whichever one you pick as M is the one you're going to have the different levels for, or strengths. Whichever one you pick as X is the one you're going to get B values for. If when you run it, it doesn't make sense, try switching it, see if it makes more sense. Always go with the hypothesis first. But just like in ANOVA, we only went across or down, not both. Same idea, only make simple slopes for one of the variables. So in ANOVA, it's called simple effects, or post hocs is the more common phrase. This is called simple slopes, because they're B values. Okay, so does that match? Books, attendance grades, books, attendance grades, sweet. So the code is moderate.lm. And what it does is it centers the variables and creates this same output, or this same linear model, where attendance in books predicts grades with the interaction, and they're scaled. But man, that's easier to type. Moderate.lm. We're going to save that as model, and then create a summary of it. I don't love the way it looks in the output, but it's not too horrible. All right, so these are main effects. Okay, this is the interaction. We're going to multiply them together. Fix this. So is the overall model significant? So this looks very similar. It's just that the labels of the group names are weird, right? Or the variable names. So yeah, it's significant. So same place. 3 and 36, 807. And then here's R squared. 0.40, so big effect size for all of the variables anyway. All 3 variables are significantly better than nothing. But are the individual variables significant? And this is where you have to remember what your variables are, and it's going to call MZ. I don't know why. It just does. Okay. So MC here stands for mean centered X, mean centered M. I think so that you're not seeing MCM. And then this is the interaction. So the first one we had, X was books. So it's significant. So for every one book, we are getting one book greater than average, right? We're getting 4 points on our grade. 36 degrees of freedom, sorry, comes from here. Because it's n minus k minus 1, so n minus 3 minus 1, so 40 minus 3 is 2.48. Equals 0.02, right? Yeah. All right, so for every increase in book, we're getting 4 points on our grade. Attendance is the next one. So every one class we go to, we're getting 1.33 points on our grade. Remember, those aren't on the same scale, so if I wanted to compare them, I would have had to z-score them. So if I z-scored the data set instead of mean centering, then they would be beta. I could compare them. But since we only mean centered, they're still B. All right, so my main effects are significant. So as the number of books you read goes up, your grade goes up. As the number of times you go to class goes up, your grade goes up. So that matches what we did when we did simultaneous regression. And then the next question is, is the interaction significant? Yes. Because otherwise this would be a terrible example. Although I do have some videos where I'm like, this isn't really going to work, but we can pretend. So it's also significant. Now, interpreting this is really hard. Right? So for every books times attendance going up 1 point, grades go up 0.73. So that doesn't make sense, right? So we have to do something to understand that interaction, because I can't interpret B directly. And that's what all of this says. So as books goes up, grades goes up after controlling for attendance in the interaction. As attendance goes up, grades go up after controlling for books in the interaction. But I don't got a good answer for what 0.73 means for grades with that interaction component. And then this is where it's confusing isn't the best word. But I don't have a good synonym. So we'll go with confusing. So we're going to create simple slopes. Most people are fine to this point as long as you're getting what regression is. So we have all this data. Okay. We've put books here, and that's why it's labeled as X, because it's the one on the X-axis. Grades here, so it's Y. And we're going to create these different groups for attendance. It's technically the moderator. In this output, it labels it as Z. Books is mean-centered, so an average number of books is here at 0 in the middle. And what I have to do is create a low group, an average group, and a high group. But we are not literally grouping them, so that's why the first line here says, do not think them as creating groups. The output looks like it's splitting into groups. So I'm not taking those 40 people and going, you're low, you're average, you're high. That's called median splitting sometimes. It's not really median. Chord thirds splitting, don't do that. X ain't bad. Instead, we're going to leave the data continuous. That gives us more power. Right. And we're just going to pretend like each individual person could be low, average, and high. So for each person, we basically take their attendance score and pretend like they're on the average, or they're below average, or they're above the average. So what that means is that for this data, we shift it around. So this is the only way I've been able to explain this, is like you're going to pretend like this person is 1 standard deviation below their score, that's for low, current score, or 1 standard deviation above their score. So you can kind of think of this like, okay, I read 3 books. That makes me average. What would my score have been if I didn't read any of those books? So I was on the low end. What would my score have been if I did read all those books? So if I had gotten a high number of books with my attendance score. We're only manipulating one of them, though. Right? So we're manipulating attendance. I'm sorry, I said that backwards, I think. we're changing attendance and looking at books. So I came to class an average number of times. What happens if I never came? What happens if I always came? So kind of pretending like people are above and below where they actually were on their score. You used to have to do this by hand, so we literally had to make those scores. But Quantpsyc does that for you, thank God, so I don't have to explain how that works, because that's where everybody went, like, what happened? But essentially, for the high group, we're pretending they're a standard deviation above their score. For the low group, we're pretending they're a standard deviation below. As long as you can get that. The reason we mean-centered, what I said, was multicollinearity, and then here's the interpretation part. So where we started was everybody was mean-centered. So that means that the very first regression you ran was like at an average level of attendance. Here's books for an average level of books. So by mean centering, we're taking those regression slopes in the main model. This is the main model. That's the average score. So books is X, attendance is Z. Right? So at an average level of attendance, people's books to grade score is 4.15. So for every, we'll do it like this. So if I'm at the average attendance level, I'll get to what does that mean in a second. Every book I read adds 4 points to my score. What happens if I didn't go to class? What happens if I did go to class more? Okay. Questions yet? This is the hard part, like understanding how it's creating these things. Not yet. Doing that thing where nobody asks questions until you get stuck on your homework 3 hours before it's due. Okay. All right. So here's my note. You can switch X and M if you wanted to. But the way you run that is this next line down. So it's sim.slopes to make the simple slopes. Model. The word model comes from the model I ran up here. So it's taking the analysis that you ran. We are mean centering. And I'm not entirely sure why you have to do this, but you do. So the attendance score. So whichever one is in M is also there. So you're basically telling which variable you want to use as the moderator. So that's why it says M here. So I'm going to run both of those. Oops, I'm going to rerun the wrong one. There we go. And you get this output. So I'll put that here. So what's going on in this output? It doesn't look like your LM output. It's a little different. AT here is for attendance. So it's telling you that this is attendance high, attendance medium, and attendance low. This is the intercept. So that's the average score. So at an average attendance, the intercept is 61 points. So people who are going to class on average are making 61s. People who are going to class less than average are making 56s. Okay. Slope here is for the other variable. Okay, this is not about attendance. We've fake split attendance up. This is books. Okay, so where it says slope, that's actually for X. Okay. Standard error. LCL's lower confidence limit and UCL's upper confidence limit. Yeah.
The mean one for the books, the slope, is that the same thing as what we got for the main effect slope?
Yes. 4.15. Yeah. That's how you can tell you did the one you wanted. So that was a sentence or two away. But yes. So what John is saying here is that average here, 4.15. So you can make sure you're using the variable you think you are. That should match the one up here, 4.15. So we're creating levels for one and looking at the other one. Just like when you run ANOVA, you split one and look at the other one. Because remember, you can't split and use it at the same time. It'll freak out. So if I'm going to attendance a high amount, or one standard deviation above average, so it creates those high, medium, and low groups by using standard deviations, my slope is 7.230. So there's an additive effect. If I'm going to class more often than normal, every book I read is 7 points, because it's adding to that attendance effect. If I'm going to class on average, every book I read is 4 points. If I'm going to class a low amount, like never, every book I read is 1 point. So you might as well drop at that point, right? Because you're not going to class and the books aren't going to help. Yeah, we'll put that one. So it creates this fan effect. If you run one of these analyses and all of your numbers are precisely the same, 4.15, 4.25, 4.0, there's no effect because you get these parallel slopes. You should run it and get different slopes. I mean, how different depends on the scale, right? But also, should create a fan. It may be a perfect X, so you may get, I don't know how a good place to draw this, but one's positive, one's negative, and one's nothing. You may get that one's slightly positive, the other two are really negative, but it should cross, is what I'm trying to say. So you should get these fan effects. We'll talk about how to make this graph in a second. Now, interpreting the slopes is the same. So at a high level of attendance, every book gives me 7 points. Average level attendance, every book gives me 4 points. Low levels of attendance, each book is only 1 point. And the only thing I don't like about this package is you don't get P. There's no knowing if this is significant. The caveat on that is we can use the confidence limits, but it is the same analysis as this one. All we're doing is moving people's scores up and down. That is a mathematically linear transform, so none of the significance values here change. Okay. The slope for attendance is never changing. The slope for the interaction is not changing. Only the one for books is changing, and the overall R-squared doesn't change. So that's why there's not a whole lot of output to look at. The only one that's changing is books. Clearly, you have the p-value for the average levels, but it doesn't really give them to you for the rest. And what we can do, so we don't have to run a whole bunch of wicked math, is just look at the confidence interval. This is mean-centered. So anything that is not 0 is good. That's another reason why mean centering is so great. Okay? Is it because the first analysis becomes the mean, and then the other two analyses, if they're different from 0, that means they're significant. So by different from 0, I mean one can't be positive and one can't and negative. Can't mix and match. These are both greater than 0, so this one's significant. These are both greater than 0, so it's significant. These are not. The 0 is in the range of credible values. I don't think we've talked about confidence intervals in a long time. So confidence intervals, remember, are the range of values you would expect the true population to mean to include, which is a lot of mumbo jumbo. So the way I think about this is that these are the range of scores that should be believed, given my sample and the standard error. And 0 is a credible score. So that slope is not different from 0. And that's an easy way to talk about, are they significant, rather than calculating a whole bunch of t-values, because that takes a lot of work. So these two are significant, and this one's not. But the interaction happened because they're clearly different. So sometimes they might all still be significant. We talked about this when we did effect sizes for interactions, where sometimes they're all in the same direction and they're all significant, but the effect sizes are one's small, one's medium, and one's huge. Okay? Same idea. This one's not significant, and these two are big and then bigger. So the effect size is changing. Now, Okay, I walked through all of this. What I mean by low levels of attendance, high levels of attendance. Because when you're talking to like administrators, that doesn't mean squat, right? Yeah.
Okay, so when you're saying that that's like not significant, that would mean that like reading books doesn't have an effect when the attendance
Is low, right?
Is that what it's saying?
Yes,
Okay.
exactly. That's why I said if you're not going to class, you might as well not read the books because it's not helping you.
So that's what the lower limit, upper limit is going to tell us is
Right, because it includes zero. One's positive, one's negative.
Okay.
Exactly. Okay, where was I going? Oh, interpretation. So I went to administrators and said, you know, if they're not going to class, they're not going to do very well. One, they would be like, duh, right? But they went, what do you mean not going to class? Do you mean never going to class? Well, how many times do they have to go before before this starts to be important for them to read? So coming up with like a number back in the original scale that's interpretable. Since this is mean-centered, you just calculate the mean, which is just kind of a quick reminder, here's how you get means, without using t-apply, because there's no t-apply, there are no groups. Okay. So we just calculate the mean and the standard deviation. And we get that an average attendance for a student in this sample is 14 points. Okay. So if they're at 14 points, every book is 4 points. If they're one standard deviation above, so here's my standard deviation, which means they're at 18 class attendance, then each book is 7 points. If they're at 16, they're somewhere between these two. Subtract here. 14 minus 4 is 10. So at 10, it doesn't matter. So at some point between these two, it starts to matter. But we don't, that's called a Johnson-Neyman analysis, and it just wasn't worth the trouble. So what you could say is somewhere between 10 and 14 classes is when it starts to matter. There are ways to analyze exactly where the interaction starts and stops. It's called a Johnson-Neyman. And it isn't super popular because it's kind of hard. So that's what I did here. So that's just a way to bring it back to the original scale of the data. Graphs are totally different. It's crazy. It's like 3 lines. So much simpler. It's not a very pretty graph, but it's good enough for government work. Right. Because making them in ggplot gave me a headache because I tried to do it for a poster we were presenting and then I gave up. So when you run the graph.mod from this package, this is all still part of Quantpsyc, it actually gives you this little stop icon when you run it because it wants you to click over here. If you click somewhere in the graph, it'll put this giant label on it that you cannot move or change. So what I've been doing is just running it, clicking somewhere outside the graph so I don't have that giant label. And then in the figure caption, I added what the colors meant. So instead of having a legend, which kills me inside because I'm like, it needs a legend, I just stuck it in the figure caption. All right. So what's in this graph? This is the picture I was drawing on the board. So this is centered books. Okay, so this is an average number of books. If I was making this for a publication, I would probably try to figure out a way to overlay and put the real scores on here. But it creates a centered books on the bottom, so this would be whatever the average number of books is. Here's my grade in the class. Each dot is the person, so this is a scatter plot. The average score is this dotted line. So if we made a graph of books to grades in class, ignoring attendance, it would be that dotted line. And then it has the low slope and the high slope. The low slope is in red, the high slope is in blue, always. So even though this analysis, the low slope is the lowest B, that may not happen. It may be that the group who has the lowest scores has the strongest slope. Okay? So don't correlate low group with low B. That doesn't necessarily happen. I think I showed you guys that analysis of like men, depression, and drinking. We were talking about how it creates this X pattern. So for men who weren't drinking or weren't depressed, it was like totally flat. And then as they added more depression, we got more drinking. Okay, so you got a different pattern depending on the data set. Well, that is a simple slopes graph. And then when you present these, you do essentially the same write-up that you would have done for a simultaneous analysis. Yes, a model is significant. Here's B, here's B, here's B. And then you have a little paragraph that talks about the slopes. It's not even a paragraph, it's like 3 lines. And I included the confidence intervals. So for average attendance, X. For low attendance, books is. For high attendance, books is. So literally it takes you like 3 times as long to run the data screening. And then the analysis is only like 10 lines. Which I feel like is normal at this point, right? But the important thing I think out of all this to get is these are not separate groups. These are just pretending as if each person were low, average, and high.